Welcome back, friends, to another session of fluid mechanics and rate processes. So we are at a very interesting stage of this course where we are trying to put together all that we have learned so far in looking at the viscous flows. Let's start. So we want to talk about boundary layers. Let me review for you what we studied about this concept of boundary layer. So let me first begin with the example of a flat plate. I'll give you two examples, a flat plate and then an airfoil. So this is a uniform flow coming into the flat plate, and then I could get a boundary layer, right? So this region is the viscous region. If the Reynolds number is fairly high, and the outer region is the inviscid region. If I try to draw a velocity profile, let's say I draw a velocity profile at this station, then what I would find is that outside the boundary layer, I have almost a uniform flow. So this is the profile. And then inside, of course, it respects the no slip boundary condition. So you have the boundary layer. Likewise, for flow past an airfoil, so if I had flow coming in to an airfoil, then I would have a region where the shear stresses are large, the viscous effects are large. And if I drew a profile, let's say somewhere here, then what I would see is some kind of an inviscid flow outside and then a boundary layer on the inside. So this region we are referring to as the boundary layer. So I should mark here. This is where the viscous effects are important. So this is the viscous region, and the outside region is the inviscid region. If I wanted to analyze any of these two flows or some flows which are similar to this, I really had two options. Option one is I take the full Navier-Stokes equations, apply my boundary conditions, which would be for a flat plate, velocity is 0 here, far away the effect of flat plate is not there, free stream conditions, and solve the full Navier-Stokes. Do the same thing for an airfoil, right? But then we have already seen how complex the Navier-Stokes equations are. They are difficult to solve. So the engineering solution to this problem is to split it into two smaller problems. We perhaps could model the inviscid region by the Euler equations, which are for inviscid flows. And these, of course, could be simplified to potential flows if I can further show that this flow is irrotational. And as we know, the potential flow is really easy to solve. Okay, only one unknown. The equation is del square phi equal to 0. And we've already seen flow past a circular cylinder, a spinning cylinder. We could do that for airfoils and so on. So this part is easy. We could do the same thing for an airfoil. And inside this zone where the viscous effects are important, we could actually get something called boundary layer equations. So I will now solve two sets of equations, the easy equations, the Euler equations or the potential flow equations. I would really like to solve the potential flow equations if that is applicable. But if the flow is rotational, the outer flow is rotational, then I would have to solve the Euler equations. And then I solve the boundary layer equations in the inside and match the two solutions. Okay, so that's the recipe that we are going to follow. So today in this session we are going to derive the boundary layer equations. I have already given you a foundation of that in the earlier classes, but today we are going to follow that up with more rigor. So let us assume that we are dealing with a two-dimensional flow, although these equations would be valid for 3 dimensions as well. We will further assume that we have an incompressible flow. We will also assume that the flow is steady. All these assumptions can be relaxed, but then the equations will become slightly more complicated at each step. So we want to avoid that and look at the most basic analysis. Okay. And we are also going to assume no body forces. So for this situation, I can now try to take the Navier-Stokes equations and then push in some assumptions and derive the boundary layer equations. That's the first thing that we want to do. We are interested in a situation where this assumption is valid, boundary layer equations are valid, and for that we will need the following. So first is, we will assume there is no flow separation. Because if the flow separates, then we will see that the boundary layer assumption itself breaks down. Then you cannot divide the flow into an outer flow and an inner flow. Then actually this kind of a difference between two regimes would become very murky, and we cannot really do that. So no flow separation. And B, we are really talking about a situation where this region is thin. Okay, so the viscous region is very narrow. That would happen, we have shown in an earlier session that we are dealing with high Reynolds number such that my delta, the boundary layer thickness, so this here for example is the boundary layer thickness. Of course, it's a function of x. Similarly, in the airfoil, the boundary layer thickness is a function of x. So we are saying that delta by L, if it's a characteristic length, for example, for the airfoil, I could take the chord of the airfoil. That's much smaller than 1. And we've seen that in an earlier session. So I showed you the thickness of a boundary layer on the wing of an Airbus A320 when it is in cruise. It was really of the order of a millimeter, very tiny. And another assumption that we are going to make is that the curvature effects are neglected. So either we have a flat surface, or even if we have a curved surface, it's a very gentle curvature. So I could actually assume that x coordinate is along the surface of the airfoil, and the curvature is so gentle that I can actually think of it as a flattened out airfoil surface. Okay? So with these assumptions, what I am going to do is write down the Navier-Stokes equations, and then we will do some kind of order of magnitude analysis, throw away the terms which are not so large as some of the other terms, and we will get simplified equations. So we will use what is called non-dimensionalization. We've done this many times before. And part of what I have done today, we have done in an earlier session, but no harm in repeating that to drive home the point. So we are going to say that x star is the non-dimensional x coordinate, and that is given by non-dimensionalized with a characteristic length of L. Y star, because we are inside the boundary layer, L may not be the correct characteristic length, it actually is the boundary layer thickness. So this would be given as y divided by delta. And we already know that delta is expected to be much smaller than capital L. Same thing with Vx. Vx star is the non-dimensional streamwise speed, which is with the free stream speed. So u is the free stream speed at far away from the body. We don't know how to non-dimensionalize Vy. So we are going to assume that this is given as something by Uy, and Uy is to be determined. In fact, that will come right out of this analysis magically. We don't know what the role of pressure exactly would be, but for the time being, let's say P star is the non-dimensional pressure, which is given as P divided by rho u square. So that's the free stream dynamic pressure. Okay, so let's write down the three equations. So first the continuity equation, then the x momentum equation, and then the y momentum equation. And we will first write the dimensional forms and then the non-dimensional form. So continuity equation, del Vx by del x plus del Vy by del y, this is 0. The x momentum equation, rho Vx del Vx by del x plus Vy del Vx by del y. So that's the convective term. Then I am going to write down the pressure term, and this is equal to the Laplacian of the x component of velocity, which is del square Vx by del x square plus del square Vx by del y square. So that's your x momentum equation. The y momentum equation, again the convection term, so this time it is Vx del Vy by del x plus Vy del Vy by del y. Then the pressure gradient, that would be del P del y, and this is mu del square Vy by del x square plus del square Vy by del y square. Essentially this term is just the Laplacian of the y component of velocity. So let me number these. This is 1, 2 and 3. Now I will try to non-dimensionalize them. So that's easy. For Vx, I am going to replace it with Vx star times u, and for x I am going to replace it with x star times L. Okay? So let's do the x momentum equation first. And you can see that would be essentially u divided by L del Vx star by del x star. That's my first term. And now I come to the second term. So for Vy, I am using Uy as my characteristic speed, and for the y I am using delta. So this becomes del Vy star by del y star equal to 0. There are two terms in this equation. Okay? They have to be of the same order. I cannot have two terms and say one term is significantly larger than the other. In fact, it has to be exactly equal to the other. So if I am just interested in the order of magnitude analysis, not their size, then I would like to argue that because this is non-dimensional, so this term is of the order of 1. And similarly, I have non-dimensionalized Vy with Uy, so therefore it is of the order of 1. Similarly, y is non-dimensionalized with delta, so again this term is of the order of 1. Order does not mean it is exactly equal to 1, but it's something like it could be 5, it could be 3, it could be 5.7 and so on. So there you go. I have this term of the order of 1, this term of the order of 1. That means these coefficients should be similar. And right away I can see that my Uy is therefore of the order of, or rather I can say order of uy is delta by L capital U. I already know delta is very small compared to L. So what this means is that my speed in the y direction is much smaller than u. So this tells me that uy is much smaller than capital U. Okay? Let's come down to the x momentum equation. So the x momentum equation tells me I am going to now take the first term, so that's rho, and for Vx I get u and then L and another u, so this would be Vx star del Vx star by del x star. So that's my first term. For the second term, now for Vy, I am going to substitute Vy as uy times Vy star, but uy I already know it's delta by Lu. Okay? So I am going to straight away write down this delta by Lu times a Vy star, and then I have for del Vx by del y as u divided by delta Vx star by del y star. Okay, that's my second term. And now I am going to write down my pressure gradient term. So that would be rho u square by L del P star by del x star. And now I come down to my viscous terms. Okay. So the first viscous term is I get a u by L square, and that would be del square Vx star by del x star square. Plus the second term would be given as, now there's a by y square, so that would be u by delta square del square Vx star by del y star square. Okay. Now I am going to divide the whole equation. So divide by rho u square by L, and let's see what I get out of this equation. So this stays as it is, Vx star del Vx star by del x star. This I get, these deltas they cancel out. Sorry, there was a rho here as well. Okay, I missed out on the rho, on the convective term. So that also goes away. So I am going to get Vy star times del Vx star by del y square. I am going to lose the coefficient here also. I have divided by rho u square by L. So this is del P star by del x star. And now I come to this term. So I will have the following. So this would be mu divided by rho, and I am dividing by u square. So there is one u and then an L, and this would be del Vx star by del x star square. Okay. How about the next term? The next term would be mu divided by rho u L. So I would like to retain this kind of a form, and the remaining terms, as you would see, are L square by delta square del square Vx star by del y star square. Great. This term, as you would recollect, is actually the Reynolds number. So I am going to write down as 1 divided by Reynolds number. So Reynolds number is defined as rho u L divided by mu. And this is also the same term. So 1 by Reynolds number. And this, of course, is a very large term because L square is going to be much larger than delta square. So let's see how we argue. Convection, pressure, viscous. We are inside a boundary layer. So viscous terms have to be important. Okay, so we cannot throw them away. Now the argument is, these are non-dimensional terms, so they are of the order of 1. Okay. Likewise, these terms are of the order of 1. Pressure also along the pressure gradient along the x direction. So all these terms are of the order of 1. I cannot have viscous terms which are larger than order of 1. Because if I had those terms to be larger than 1, then I must have something to balance them. Okay. So otherwise this equation is just not going to work out. Okay. So I will have to have both these terms of the order of 1 or less. Of course, one of these terms could be very small, but both viscous terms combined should be of the order of these terms to balance the equation out. Okay, let's argue. This is of the order of 1, I suppose. But then this term is extremely small because my Reynolds number is very large. So this term is very small, 1 by Re. On the other hand, this L square by delta square is very large. So therefore this term I can drop because this is much less than 1. And I would like the viscous term to be of the order of 1, and if this term is of the order of 1, then I can conclude that the product of this and 1 by Re should be of the order of 1. So therefore this implies, these two terms, they actually imply that L square delta square times 1 by Re should be of the order of 1. Which really means that delta by L is of the order of 1 by square root Re. So magically, just from non-dimensional analysis, I am able to get what is the thickness of the boundary layer, and that turns out to be very small. Okay, delta by L is varying as 1 by square root of Re. And we did see this in one of the earlier sessions, that for the wing of an Airbus, okay, this was of the order of a millimeter, when the chord of the wing was of the order of several meters. Let's now work with the y momentum equation. It will be exactly the same thing. We'll take the dimensional form and then non-dimensionalize it. So the first term there is rho times Vx. For that I am going to write down u times Vx star. And for the Vy, it is Uy by L del Vy star by del x star. So that's the first term. And let me simplify this right away. This would become rho u, and here I would get Vx star del Vy star by del x star. And I'll substitute for Uy. Uy is given as delta times u by L. Okay, so that's what I'm going to get for this term. And then the next term would be plus rho delta u square by L square Vy star del Vy star by del y star. For the pressure term, I am going to get rho u square by L by delta actually, because now I have del P star by delta y star. And then I have to write down the viscous terms. They are going to be delta u by L cube del square V y star by del x star square plus the second derivative of the y velocity, which would be u times delta by L delta square del square Vy star by del y star square. Okay. For this equation, what I'll do is divide everywhere by this quantity, which is essentially rho u square by L times delta. Let me make some space. So this would give us, so I am continuing on the y momentum equation. So all I have done is taken the equation up there and divide everywhere by rho u square delta by L, and I would get the following: Vx star del Vy star by del x star plus Vy star del Vy star by del y star. So that's the convection term. Then the pressure gradient term, which would be L square by delta square del P star by del y star. And then here I would get, I will already substitute for the Reynolds number because you are aware of it now, del square Vy star by, that's the first term, and then the next term would be plus 1 over Re delta square by L square times del square Vy star by, this I am sorry is x square. So this is your non-dimensional equations. Let's number these terms. So this I will call as T1, this as T2, T3, T4, T5. I want to argue which of these terms are important. Okay, that's the question I want to ask. So these terms are obviously of the order of 1, no doubt about that. Similarly, T2 is of the order of 1. Okay. I already know that this term over here, del P star by del y star, if it is of the order of 1, then the coefficient L square by delta square is very large, and this would become extremely large. That cannot happen. So this term has to be maximum of the order of 1. Okay, so this entire term has to be of the order of 1 at the most. And what that would imply is that del P star by del y star is actually of the order of, so if I look at the order of this term, this should be the inverse of that, so it should be delta by L whole square, which is actually much, much less than 1, because delta is very small. As you know, delta by L whole square is of the order of 1 by Reynolds number. So I am able to conclude from this that if these are the convective terms and the pressure terms have to be at the most of this size, they cannot be larger, then this del P star by del y star has to be very small, and therefore what it means is that the pressure variation across the boundary layer is negligible. Okay? So this term actually implies that pressure variation across boundary layer is negligible. That's very interesting. What it tells me is that if I have an airfoil and if I had a boundary layer, then whatever, if I took a section here, then the pressure across the boundary layer, that means the variation in the pressure here, is negligible. So whatever is the pressure I feel at the edge of the boundary layer is going to be the pressure that I feel on the airfoil itself, which really means that if I did not have a separated flow, it's an attached flow, then if I am able to compute or estimate the pressure through a potential flow analysis or an inviscid flow analysis, okay, that actually holds even at the edge of the boundary layer. So it's a very important conclusion. Let's come back to these terms. I already know that these two are the viscous terms and they cannot be larger than order of 1, okay, because that's the maximum that I can have. Out of that, this term is very small because it's of the order of 1 by Re. So this term is small because of 1 by Re. This term, on the other hand, could be important, okay, because I have delta square by L square varying as 1 over Re. So in fact this term also would be very small, okay. So this term is of the order of 1 by Re, okay. So overall my conclusion from this equation is it doesn't give me anything meaningful, okay. The only thing is it tells me that I will use the fact that del P by del Y can be neglected. Okay. So now let me therefore write down the boundary layer equations for you after this analysis. So let's now write down what are my boundary layer equations. So the first is the continuity equation. There is no change to that. It remains as is. So I get del Vx by del x plus del Vy by del y equal to 0. Then I have the x momentum equation and I have the y momentum equation. Let me first write the y momentum equation because that's fairly simple. This we have seen tells us that del P by del Y is 0 inside the boundary layer, which really implies that P is only a function of x. So I can replace del P by del x with dP by dx. How about the x momentum equation? I'll have to retain the convection term. So the first term is Vx del Vx by del x. The next term is Vy del Vx by del y, and of course they have to be multiplied with the density. Then I have the pressure gradient, but this time I can write it as dP dx simply because my pressure is only a function of x. Next I come to the viscous terms. So I have shown that the first term, which is the del square Vx by del x square, is negligible, so no need to keep it, and we are going to get del square Vx by del y square. Okay, so these are your boundary layer equations. They are much simpler than the full Navier-Stokes equations because you can see pretty much we have now two main equations. The third one is really already taken care of in this equation. Okay. What about the boundary conditions? For the far stream, the same conditions as in the Navier-Stokes, but there is no far stream here. Okay, we are inside the boundary layer. So therefore, the conditions that we really need to apply are on the solid surface and at the edge of the boundary layer. So let me write that down. So on the surface, we are going to say that the velocity at y equal to y surface, or maybe I should say x equal to x surface, this is the body surface, would be same as the velocity of the body. In fact, if it is a stationary body, so for stationary surface, I would have to satisfy the no slip boundary condition, and then my Vx is 0 and my Vy is 0 on body. Then I have to have an additional boundary condition at y equal to delta, at the edge of the boundary layer. And there the condition would be that my speed at y equal to delta at every x should be actually the free stream speed vector times 0.99. So at the edge of the boundary layer, the flow achieves 99% of the free stream speed. So I'll have to solve these two boundary layer equations along with these two conditions. Okay. Let's see what happens for a flat plate. For a flat plate, I have some simplifications. First of all, my pressure gradient dP dx is 0. Okay? So I can get rid of this term. So my equations become del Vx by del x plus del Vy by del y 0, and then I have rho Vx del Vx del x plus Vy del Vx del y. This is mu times del square Vx by del y square. These are the equations that govern the boundary layer on a flat plate. And my boundary conditions would be simply that Vx equal to Vy is 0 at y equal to 0. That's the surface of the plate. And Vx equal to 0.99 times the free stream speed at y equal to delta. One would expect that this equation is easy to solve. Unfortunately, no. It needs a numerical solution. So the solution was proposed by Blasius, and that's why it's called a Blasius boundary layer solution, using self-similarity. He made a very smart observation. What he argued is the following. He said that if this is my flat plate and the horizontal axis is the x-axis, that's my y, then I would get profiles at different locations. So that's my boundary layer here, and of course far away it is a uniform flow. And as my boundary layer thickens, so let me draw a profile here, then I would have the same free stream, but now I have a thicker boundary layer. So this is the boundary layer thickness at this location, and this of course is the boundary layer thickness at another location. So he argued the following. He said that if I non-dimensionalize y with delta, so let's define eta as y by delta. So I take, instead of the y coordinate, I take eta for this, So it will always go from 0 to 1 inside the boundary layer. So you can see eta is going to vary between 0 to 1. And I am going to define my f as Vx by u. Okay? And this also f will go between 0 and 1. So there is no flow separation, and I am assuming that the speed is 0 here, and of course it is close to 1, 99% of 1 at the edge of the boundary layer. He argued that if I plotted these f as a function of eta, okay, then this does not depend on x. So I could get the same profile, a template, and I just keep on expanding it by using a delta, and I can get a profile at different values of x. So that's a very smart thing he did, and he simplified these equations further. I am not going to go into the details, you can read that up. And what he was able to show is that with this analysis, found a numerical solution. In fact, he was able to reduce this problem of partial differential equation into an ordinary differential equation. Okay, and he was able to solve that on a computer. So he was able to show that tau wall, which is the shear stress, which of course is defined as mu del Vx by del y at y equal to 0. This is given as 0.332 times rho u square by square root of Rex. So he defined a Reynolds number based on x, which means if this is my x, then I can define a Reynolds number x as rho u x by mu. Okay? And that's what he found the tau wall to be. From this, he was able to come up with Cf, which is the skin friction coefficient. And you all know by now what is the skin friction coefficient. It is the non-dimensional tau wall. So tau wall, it is non-dimensionalized with half rho u square, the dynamic pressure. And this we can work out would be 0.664 divided by square root of Re. Once I know this, then I can ask myself, what if the length of my plate is L? Okay, so I drag a plate through water, and I want to find out what is the frictional drag or the resistance it will encounter. So I can use this formula, and at least for one side of the plate, okay, if both sides are exposed, then of course you would have a boundary layer on the upper and lower surface. But assuming that only one side is exposed, I can actually calculate the drag coefficient. So let me do that for you. So what he was able to show is that CD is the drag coefficient on a plate of length L, and suppose its width is B. Sorry, B, small b. So B is the depth of the plate inside the blackboard. Then this would be equal to the force, the drag force that the plate feels, divided by half rho u square. So that's the dynamic pressure, non-dimensionalized with an area, and the area I would take as L times B. And FD is the drag force that would simply be integral from 0 to L, the shear stress on the plate times the area, which is B because it's the depth of the plate, times dx. And I can work this out. So you can put in the expression for tau wall that I have written over there, and what we will find is that CD will be given as 1.328 by square root of REL. So that's the skin friction resistance to a plate. So if I pull a plate, or in other words, if I have a plate over which there is a uniform flow, then the drag felt because of the skin friction is given by this expression for one side. So this is for one side, one wet side. If both sides of the plate are encountering the flow, then of course you would have to double this. Great. A question that you could ask is, what happens if my plate is extremely long? Okay, L is very large. Then just like in a pipe, the flow could actually become turbulent. So flow can become turbulent beyond a certain RE. In fact, what I would like to show you is that if I take a flat plate and I draw a boundary layer on it, what could happen is I could get a laminar boundary layer, and then after some time it goes through some transition, just as we saw in flow inside a pipe, the experiments of Professor Osborne Reynolds, and then you could have a turbulent boundary layer. Okay. Now, where exactly the transition begins and it ends depends on a variety of things, just like we saw in the pipe. It would depend on the speed of the flow, for sure. It would depend on the viscosity of the fluid. It would depend on the environmental conditions, how about the vibrations, and it would depend on the roughness. How rough is your plate? So this could occur at a small distance, or if you make the plate extremely smooth, then it could occur far away. In fact, I want to show you for a wing of an aircraft. This is often a problem. So if you look at a top view of an aircraft, suppose this is my wing. Airflow comes like this. This hardly looks like an aircraft. I am sorry for the poor picture. Some sweep back. So if it's a aircraft in cruise, you are going to get an attached flow on the wing of the aircraft. Okay? Hardly any flow separation. And whether you have a laminar flow or a turbulent flow would determine what is the drag of an aircraft and therefore the fuel that you consume. Ideally, you would like the flow to be laminar, and I will show you in a moment that the drag coefficient for a turbulent flow is much larger than for a laminar flow, okay, for a flat plate. Now, if you have the surface which is dirty, so I am a pilot, I fly the aircraft and I land, and perhaps some insects get stuck to the wing of the aircraft or some dust particles, and then I take off again without cleaning my wing. It could be dirty. Then what could happen is my boundary layer could become turbulent right here. So this is the turbulent part and this is the laminar part. And I would incur a huge drag. Versus if I polish or wash my aircraft nicely before another takeoff, keep it clean, it's possible that I may get laminar up to a long point and turbulent a little bit later. Okay? So we have not changed the design of the aircraft, we have not changed anything, but simply by maintaining your aircraft clean, you can actually affect the transition point and save on the fuel. Okay, so let's talk a little bit very briefly about the drag coefficient that one would expect on a turbulent flow past a plate. So I'm not going to give you too many details, but I'll just show you a possible velocity profile and then give you some expressions. If I did the following, if I tried to plot what is Vx by u versus y by delta. Let's say this is 0, this is 1, this is 1. Then we have seen that for a laminar boundary layer, perhaps I would see a profile like this. So this is laminar. Okay. What is the kind of profile that I would see for a turbulent flow? It turns out a turbulent flow is much thicker. So this is delta. So delta for turbulent flow is usually larger than delta for a laminar flow for the same Reynolds number. Okay, so if I somehow maintained a laminar boundary layer at a given Reynolds number and I allowed the boundary layer to become turbulent for the same Reynolds number, then the boundary layer thickness is larger for the turbulent boundary layer. But here I have non-dimensionalized it. Okay, it's both are with delta. So this is the laminar profile. How would the turbulent profile look like? Actually, it is very steep near the wall. So you would get something like this. And then it kind of does this. So this is turbulent. Okay. So right away you can see that if I looked at the skin friction, which is mu del Vx by del y, then mu of course is same whether the flow is laminar or turbulent, that's the viscosity of the fluid. But the del Vx del y, the velocity gradient, is much larger for the turbulent flow. This is much steeper. I must caution you, this is the distance and this is the speed. So be careful when you calculate del Vx del y. So this is much steeper profile, so it has a much larger gradient. So therefore the skin friction because of a turbulent boundary layer is expected to be much larger than the skin friction for a laminar boundary layer. Okay. So this is what would happen on the plate. I would have a certain drag coefficient for this part of the plate, and for the same part of the plate in the turbulent flow, the drag coefficient would be much larger. How about the expressions? Typically, a turbulent flow has a power law velocity profile. So velocity profile for turbulent boundary layer on flat plate. Obviously, I am not deriving this, I am just giving you an expression just to expose you. So typically it would be of this nature, Vx by u, that's the non-dimensional x velocity. This would vary as y by delta. With the power law, the coefficient is 1 by 7. And this coefficient can actually change. It would depend on the roughness of the plate. So to give you an example, if I look at the atmospheric boundary layer on Earth, so I could measure, for example, the boundary layer in a large field which is extremely clean, very flat. So I would get 0 speed on the ground, and then as I go up a few hundred meters, then I would see larger speed. Okay. I would get a boundary layer profile very similar to what we have drawn earlier. Okay. So that would be one profile. Now I make a measurement, let's say, in a city area where there are buildings, there are trees, there are small hills. And there the profile could look different because there are so many obstructions. Okay, so both are turbulent flows, but the profiles could be different. Okay, so they act, the trees, the buildings, they would act as roughness elements. Okay, so this is one example where you get a power law profile. Typically, if I look at my delta by x, that would vary as, let's say, 0.35 Reynolds number of x raised to minus 1 by 5. And if I assume that my flat plate has a boundary layer which is turbulent right from the beginning, so this is all turbulent, and this is my x. Okay, so this is my boundary layer, the flat plate. Then it is possible to show that my CD for the turbulent is something like 0.072 Re raised to minus 1/5. Just to put this in perspective, if I draw a diagram, so this is my Reynolds number and this is my drag coefficient. This is what I would see for laminar. On a log scale. So I am plotting on a log scale. But if you see for a turbulent, then it would look something like this. This is for smooth. So at a given Reynolds number, my turbulent flow has a much larger skin friction resistance compared to a laminar. And then if I take roughness, then I would get different curves. So this is how I have increasing roughness. So if you remember the Moody's charts that I showed you for flow through a pipe, okay, as we increase the roughness of the pipe, then you would get a larger skin friction, a larger resistance. The same thing happens for a flat plate. Okay, very, very similar. So if you had a very rough flat plate, you would get more drag. If you had a smooth plate, then you would have less drag. And of course, if you are able to maintain a laminar boundary layer, that's the best, you would have very low skin friction.